Standard network scanning tools and centralized logging servers are loud. When a system actively pings devices or writes traffic logs to a central database, it generates a massive, easily traceable forensic footprint. If we assume the host network architecture is actively hostile, monitored by deep packet inspection and intrusion detection systems, generating that traditional footprint results in immediate compromise. To survive in a highly monitored environment, an intelligence framework must bypass the infrastructure entirely, transferring data silently across the physical layer. We are going to trace the construction of a custom stealth telemetry pipeline. We will follow its evolution from a set of simple, local Python discovery scripts all the way to an architecture capable of complex steganographic exfiltration. By the end of this pipeline, highly sensitive raw hardware intelligence is completely obfuscated, disguised, and transmitted as nothing more than RGB color values. Real-world evasion at this scale relies on abandoning standard network protocols in favor of behavioral mathematics and decentralized physical layer transport. The foundation of this pipeline begins with a series of independent Python scripts. These act as isolated sensors, parsing network interfaces and collecting raw system metrics from local targets. These modules extract specific hardware telemetry, identifying exact radio frequency capabilities, operating bands, and raw power states like battery versus AC voltage. This follows the engineering philosophy of a decoupled, event-driven sensor architecture. Every data gathering function is siloed into its own distinct operation. Because the modules are isolated, a crash in the RF analyzer does not take down the power monitor. The architecture prevents cascading system failures in unpredictable environments. This schematic details the orchestrator layer. It sits above the isolated sensors, acting as a unified collection point to catch the disparate data feeds and collapse them into a single, structured JSON dictionary. Synthesizing these disconnected scripts into a single dictionary transforms raw, chaotic sensor noise into a unified telemetry profile. The data is now properly formatted for rigorous mathematical analysis. Machine learning models cannot interpret raw string data. A classifier does not know what words like battery or indoor mean. This matrix visualization illustrates one-hot encoding. It takes those categorical hardware parameters and converts them directly into numerical feature vectors. This mathematical translation establishes a distinct, quantifiable behavioral fingerprint for every mapped device on the network, plotting them into distinct clusters. When a completely new, undocumented hardware asset connects, we lack a static signature. We solve this using cosine similarity. As shown by this expanding formula, we calculate the exact geometric distance between the new unclassified vector and our existing clusters. By measuring that distance, the system performs zero-shot classification, identifying the new asset purely by behavioral association. If a known device's telemetry suddenly changes, for instance dropping AC power for battery, its vector physically drifts from its cluster, triggering an anomaly alert. Mapping behavior as mathematical distance, rather than relying on easily spoofed MAC addresses, creates a highly resilient, dynamic security posture. Pure hardware classification has a distinct limitation. Knowing an asset is a smartphone is entirely different from knowing who is holding it. To bridge this gap, the pipeline pivots. The orchestrator integrates external open-source intelligence, or OSINT, directly into the local telemetry data. Here we see the first step. The system intercepts captive portal authentication requests during network handshakes and extracts the target's hashed email string. Pulling these hidden email tokens provides the first concrete link between an anonymous piece of hardware and a digital identity. Simultaneously, the pipeline extracts EXF metadata from intercepted image files passing through the local network. Identifying the exact camera model and its embedded physical coordinates establishes a hard geographic anchor for the target. The pipeline then feeds the target's IP address into the Shodan API, cross-referencing the device against known open ports and CVE vulnerabilities. If the hardware is a legacy, unsupported IoT device, the orchestrator queries the Wayback Machine API to scrape historical documentation and retrieve default credentials from dead forums. These disparate intelligence feeds, the authentication hashes, the geographic coordinates, and the historical vulnerability data are compiled into a singular identity profile. Fusing localized network traffic with targeted external API queries effectively bridges the gap, turning an anonymous local MAC address into a fully de-anonymized threat profile. Exfiltrating this dense, compiled intelligence payload back to an operator across a monitored network carries extreme risk. Standard encryption is easily flagged by deep packet inspection. To survive, the system must completely obscure the format of the payload itself. The pipeline uses k-means clustering to quantize the massive telemetry arrays and OSINT files into highly dense data blocks. As illustrated here, the system utilizes a Python bytes I/O stream. It mathematically maps these raw text and hex clusters directly to precise RGB color values. The resulting output file appears to standard network firewalls as a perfectly normal, harmless PNG or JPEG image. This steganographic method ensures that even if a human analyst intercepts the transmission, they see only a pixelated image, unaware of the dense data structures hidden inside. On the receiving end, the visual data passes through a custom ResNet neural network, which perfectly reverses the process, extracting the original raw text array. Treating telemetry exfiltration as an image segmentation task forces the network's own defensive algorithms to misinterpret the intelligence payload as a harmless visual asset. Even with steganographic obfuscation, standard internet protocols leave unavoidable metadata trails regarding source and destination IP addresses. To eliminate this tracking, the pipeline leverages Meshtastic and localized LoRa architectures, completely bypassing traditional internet service providers. Implementing onion routing circuits across these decentralized radio frequency meshes eliminates the concept of fixed, trackable exit nodes. The data simply hops unpredictably from radio to radio. As a final layer of physical security, the network utilizes channel state information, or CSI, to measure the actual physical disruptions in the local radio frequency. The nodes measure the disruption of the ambient radio waves, detecting physical movement in the room and altering transmission behavior before a physical breach occurs. Combining physical layer intelligence with decentralized RF mesh routing creates a tactical communication channel that operates outside the reach of centralized internet traffic analysis. The architecture integrates basic local socket scripts into an advanced steganographic intelligence framework. This dark mode, base64 encoded dashboard is the final endpoint. It processes the decoded threat intelligence offline, rendering the geographic heat maps and telemetry data cleanly for the human operator. By integrating behavioral machine learning with physical layer radio architectures, the definition of network intelligence moves completely beyond the boundaries of the traditional internet stack.